welcome back to science. Today we're going to talk about the Doppler effect. Hey, we're going to start off with a little experiment. Well, here's how this is going to work. I'm going to run out to the parking lot real quick. I'm going to set my phone up on a little sign on the signpost out there that says no U-turns or whatever it says out there. And then I'm going to drive by with my horn blaring. And hopefully we'll see what the Doppler effect is all about. If you'll look here at this side picture, we'll get a little graphic interpretation first. Okay, so if you look at these waves, now we're going to pretend these lines around the car, I guess it's a police car, the siren are waves, right? And normally when waves come out from a point, they come out at like even intervals. Well, as the car is moving forward, what happens is it creates a wave, and then it gets closer to the other wave and creates a wave and gets closer and gets closer. And so what happens is the waves on the front of the car become bunched up. Well, that's a shorter wavelength. Shorter wavelength is going to be a higher pitched sound. The waves where the car is going away, it makes a wave and it's moved away, makes a wave and moves away. They get spread out, right? They expand a longer wavelength. Longer wavelength, lower pitch. And so what we're going to see with the Doppler effect is that, which is that sound we realize when something's coming towards us, it makes a higher pitch sound. When it passes it at lower pitch. So let's just go outside right now and take care of it. Okay, now what I'm going to do here is I'm going to set up my phone, and I'm going to get in my car and I'm going to drive by honking the horn. And what you're going to see is the Doppler effect. Now the Doppler effect is the shift in, or the change in the pitch as something making a noise comes towards you. And also, it gets higher pitch when it comes towards you, and then when it goes away from you, it's going to get a lower pitch. So I'm going to set this phone over here, kind of facing that way. There goes Mrs. Bryson. All right, I think, here we are. Okay, and I'm going to get in my car, and I'll be back in just a second. Okay, we'll go in there and edit that down a little bit and see how that turned out. See you in a few minutes. Okay, now we will put a little definition here, some more definitions on here, so we have something a little bit more concrete here to talk about. So the Doppler effect is going to be the change of that wavelength. Right? Change of that wavelength as the object's coming towards you. Right? And so when it comes towards you, the waves become lower, or become shorter, which is a higher pitch, and the waves become longer, which is a lower pitch. Okay. When we're talking about sounds, because we notice it with the sound, right? Again, as it's coming towards us, higher pitch. As it's going away, the lower pitch. All right. Now, this can also happen with light. Now, light's moving a lot faster than sound, a lot faster. And so on Earth, we're not going to notice this. Our brains can't comprehend this difference. but computers can, right? And what we notice is that the stars in the universe, oops, that's my picture here. The stars in the universe all are showing a little bit of Doppler effect when they're light. Each element, as it's being used in the star, fusing the star, remember we did that flame test? Each thing has its own color. Each element has its own unique spectra, which means its color, its light that it's putting out. And what scientists have noticed, that stars that are moving away from us have a lower, lower energy, right? Lower wave, a longer wave. Weird little glitch there. I'm going to try to start where I was. So if I'm off a little bit, I'm sorry about that. If I repeat myself too much, I'm sorry. Okay, so what I was saying is the stars that are moving away from us have a little bit longer wavelength, which we see a longer wavelength would be a red color, right? Longer waves, red's longer, purple's the shortest. And if it's coming towards us, it would have a purple shift, right? And so the stars would look more purple. Now, again, we're not going to be able to pick this up with our eyes because it's just too close, but the computer can tell the difference. They know what they're supposed to be. They're slightly off. And the conclusion of all this is that every single star in the universe is spreading away from each other because the universe is expanding. So let's see what our notes say here. So what we're saying is that we could have either, I said purple shift, I guess blue shift, purple. Okay, so the colors change because of the Doppler effect also. We can't tell with our eyes. All the stars that we can see have this red shift, right? If they're orbiting around, right, they can tell because it's going to be getting, when it comes towards us, it would be bluer. When it goes away, it would be redder. And so they can see these little fluctuations. But for the general part, objects are getting further and further away. All right? And so the universe is expanding. Now, let me look at these other pictures here that I kind of skipped over. Oops, come here. This thing is really laggy right now, and hopefully I don't crash again, but I think I'm going to. Okay, again, move out of the way, Mr. Arnold. Okay, so when objects are standing still, this is like one of those little bugs you see in the water, right? Little bug in the water. When the bug is sitting still, the waves come out evenly, and we said that before. If the bug is moving in one direction, and sometimes you can think this, right? If it's moving in one direction, the waves are going to bunch up in the front. It's going this way, so the waves are going to bunch up in front of the bug, and they're going to spread out behind it. Now, if that were sound, high, low. Have you ever been in a motorboat and they have the no wake zone, right? And you're going really slow in the water, the boat is following this pattern, kind of. Okay, now, we're going to keep changing here. If, this is dramatic because I have it concealed. If you're moving the same speed as the wave, no, this is a plane, and this is sound waves this time, right? What happens is the plane will go as fast as the wave, and so when you go as fast as the wave, they keep making new waves, and they're pushing against each other. The wave can't go any faster than it's already going. It's going the speed of sound, and if the plane is going the speed of sound, you end up with this wave barrier that forms. It's constructive interference. Remember, the waves add together, and it's on the front of the plane, right? This is why planes have problems going faster than the speed of sound. It's like when you water ski. Now, I don't know how many water skiers we have in this group, but if you water ski, or maybe inner tube, right? You've been on the back of most people have been on the tube behind the boat, right? Well, think of that. You're on the tube behind the boat. When the boat's going slow, that thing is, really hard it's getting weird, right? But as they go a little bit faster, maybe the person driving is going just a little bit, not fast yet, but just a little bit fast before we really start. The inner tube comes up, and there's a huge wave starts to build in front of the inner tube, right? And you think, oh my gosh, I'm going to sink. And all of a sudden, they gun it. And then the inner tube shoots over that wave, and you take off. It's the same thing we have with the planes. That big wave that's in front of you when you're on this inner tube, or if you're in skiing, you're in the skis and you have your feet up like this and you're holding the rope in between your legs, and the boat starts to go a little bit faster, and then all of a sudden this big wave is in front of you and you think you're not going to make it, and then all of a sudden you shoot over it, right? That big wave is this same wave. Now, this picture here is a bullet. Now, this is like I don't know what kind of bullet, probably from like a handgun or something. I can just see from it's not a high-powered rifle, though, just like a handgun. Now, look what it is. If you saw this and you didn't know what it was, you might think, you know what? That could be a picture of a boat underwater, right? It's just the way they did it. Now, what they did was use this high-speed film. And it's real sensitive, and what this high-speed film could tell is the different, I don't know exactly how they do it, but the different levels of compression of the air, which means that wave, right? And look at this. This is all the turbulence behind that bullet that's traveling through there. But let's look on this side. See that big curve in front? Right? Right over there, right? That is the shock wave or the sound barrier. When they first tried to, this is the Civil War, I believe. They were trying to shoot cannonballs a little bit further, because if your side can shoot a cannonball farther than the other side, you're going to win that battle because you can be closer than them. You can shoot over their level, right? And you can keep inching closer and you can shoot farther. So they had scientists trying to figure out how to shoot cannons further. So what are they going to do? Shove more gunpowder in those cannons, right? And so the more gunpowder you shoot in that cannon, the faster that cannonball goes, or the farther that cannonball goes, right? The faster and farther. Well, no. It hit a limit. It would only go so far. And they could put as much gunpowder as they want, almost blowing the cannons up, and it wouldn't go any further. Hypothesis. Some invisible barrier is keeping it from going any faster. Maybe it's the limit of how fast things can go. I don't know. But then they called that the sound barrier because they knew it was probably from a sound wave. Okay, let's move on. We talked about that already. I skipped ahead. Now, this is a plane again. Now, obviously, we know that planes can now go faster than the speed of sound. So can bullets. But not all bullets, but some can. Let's start with this and I'll cover this up. So our first two, right? The first one over there, the wave is going slower. The plane is going slower than sound. And it looks a lot like, the bug going across the water. Second one, that plane has reached the sound barrier. Okay? What pilots would find was this. They were flying in dogfights, and this is in World War II. And they would go in these dives, because their planes weren't designed to go faster than sound. They couldn't do it. They'd go in these dives, trying to get away from someone who was attacking them. And what would happen was they'd reach this sound, and the plane would start to shake and fall apart almost, right? Because they couldn't get over that wave. The plane's their own shape. Now, water skiers, tubers. Look at this pattern. Pretend you're on water skis and you're being dragged behind a boat, it's the same pattern. It's just, this is three-dimensional cone, but it's a plane, right? But in water, this is two-dimensional. You're on top of this, right? We call these the wakes. And if you're water skiing, some people are really good water skiers. I lost my picture there. They're really good water skiers, and they try to jump from over the wakes. Right? Not me. I'm like, but some people try to jump over those two big humps. And if you come out here, it's real smooth, right? If you're in here, it's real smooth. But these two are huge waves. Same pattern, right? What did that boat have to do to go over that? They had to gun it over that initial wave, and then it was going faster. The boat had no problem. After it went faster than that wave, there was no big wave in front of it anymore. Now the waves are going to be behind it. It's making a new wave, and it's moving on. It's going faster than those waves, so those waves can't get ahead of it to slow it down. I hope that makes sense. Now, Chuck Yeager. Chuck Yeager was the first person to fly a plane faster than the speed of sound. And this is the plane they used. Now, this is hanging up in the Smithsonian, if you ever go to Washington, D.C., and it's hanging in the Air Space Museum there. And you look at it, you'll see it, you'll be like, oh my gosh, that's that plane. You'll recognize it in a second. I mean, it's bright orange. This is not a jet. This is a rocket engine in this. This is like the beginning of space flight. They use these things what they would do is this plane does not take off by itself. They put this plane in a bomber, and then they fly up into the high atmosphere, and they drop it out. They drop it from the bottom of the plane, and then they kick on these big rocket engines. In the beginning, it still couldn't go faster than the speed of sound. And they had to do some stuff with the tail. The tail, moves and shifts, because to go faster than the speed of sound, they have to be this shape. They have to be this long nose, pointy shape that can cut through that barrier. They can't have it. They have to have little teeny short wings. You see this thing, the wings are not, well, they're longer than that, but the little teeny short wings or swept back wings, because they can't have anything sticking out, because they can't get over that barrier if they do. Now that is the shape of, if you guys have a high-powered rifle at home, right? Look at that shape. It's the same shape as the high-powered rifle. Those high-powered rifles, with those big long bullets and stuff like that, like a 22-250 or whatever you have, those bullets can go faster than the speed of sound. But it's because of that shape. Should be in the next picture. Oops. Here's the same thing. They're showing the wave. They call it the bow wave, or they call it the shock wave. We call it the wake. All sorts of different names. All right, here's the bullet picture. So this could be a high-speed boat underwater. If you're underwater and you see a high-speed boat, right? But this is a bullet. Again, look at the turbulence behind it. But look at the lines. The lines are touching the nose, and they're in a V shape. There's actually two of them, right? And so they're in that V shape. And what's happening is they are going faster than the speed of sound, and so they create that wave bow, that thing you would see if you were water skiing again. Right? And the bullet sound, right? High-powered rifle. You hear the breaking of the... Now, I shouldn't say. When you hear the sound, that's not the breaking of the sound barrier. It's not an explosion when you break through this barrier. You're hearing the barrier itself. You're hearing the wake from the motorboat. You know that big wake, that big wave? That's what hits your ears. That's all that sound combined together. And what happens when you hear all that sound together? It sounds like an explosion. It's not an explosion. It just sounds like an explosion because what is an explosion? A shock wave. What is this thing? A shock wave. And so, breaking the sound barrier creates this really loud boom. Sonic boom. Not an explosion. Not really breaking anything. Just creating this wave pattern. Here's a picture of I think this is an FA-18. My brother used to fly these. It's above the ocean. It's a Navy plane. It's going just a little bit faster than the speed of sound. It doesn't mean that it's just breaking through it right now. It just means it's going faster. This shock wave, where this little cloud is forming, is because that's a pressure point. What happens when you put water vapor, very humid conditions, in a pressure point? You're going to create a little cloud there because of the pressure. This is another one of those pictures like the Bullet with the high-speed camera, whatever they use. And this plane, I think this is a Blackbird, I'm not sure. But look at the shock waves. Look at the shock waves. They're using some kind of filter, right, to do this, but you can see the shock waves. The steeper the cone, the faster that plane must be going. Here's another plane. Now this one's not going quite as fast. What's it say? 1.1. But look at that. You can see it. It's right on the edge. You can see it's almost like the barrier, and then you can see the shock waves also. Here's a nice cartoon picture. A little bit easier to see sometimes. Right? Oops. What did I just do? I just crashed. Time out. Mirror. Coffee break. Okay, I'm back. Again, it was just it looks like a cone, right? And that's the shock wave or shock cone. I've seen videos where they show supersonic planes flying over fields, and it just levels the grain, whatever's out there, like a wheat field, and it'll smash it all down. Oops. I have something weird going on here I don't know how to do. I have two screens. All right. And last but not least, we're about done, so maybe I won't be able to finish with a picture on here. But this is, well, it was the world's fastest car. I think it may still have the record. But you look at this thing, you can see that this car is also driving faster than the speed of sound. Now, this is in the Salt Flats. And look at the shape. It's the same pointy shape. Nothing sticking out. It's a big rocket engine on the back of this thing, or jet engines. I don't remember exactly which one this had. But you can see those shock waves right through here. Okay, let's get back to see if I can get my picture back on here. Boop. Hey, there we go. So, to conclude, Doppler effect, changing the pitch as you travel, right? The sound waves bunch together, higher pitch when it comes towards you. When it goes away, lower pitch, they spread out. We take this to the extreme. That means going the speed of sound. Those waves bunch up and form a wave barrier in front. Very difficult to get through. If you can get through, you need a lot of power, and you need to be shaped like a high caliber, high powered rifle bullet. Getting through that creates that shock wave, that shock bow, or the wake as we call in water skiing, and the constructive interferences on the side. That wake, that big wave, if you were there in your inner tube floating along and a boat comes by really fast and the big wave hits you, that's like if the plane went by supersonic and you heard what you thought was an explosion. That's a sonic boom. It's the wave. It's not an explosion. It's not breaking anything. It's just the waves, just like the wake of that boat. That wave, though, is strong enough for a plane that's supersonic that it can break windows. Resonance, right? Sound waves, powerful. If it resonates exactly right, or the shock is enough, it can break windows. That's why they don't let supersonic planes fly over the land, because they don't want to break people's windows out. Now, the only people that can do it are the military, and they do it at a very high elevation. And if you go out on a Sunday afternoon, sometimes you can hear the planes way up in the air. They're military planes. I don't know how far away they are. You rarely see them, but you can hear them. Sometimes you can see them if it's real clear. And if you're lucky, and it's always on Sundays, I think they're practicing. It's probably the National Guard practicing, like a Sunday, every once in a while in the summertime. And every once in a while, you can hear a sonic boom. Try it out. Okay. I think they're flying probably from Toledo to Dayton or something like that. You know, they're going to go over Upper Sandusky, and you're going to hear it. Okay, I'm done for the day. Fill out the worksheet. Hopefully you filled out the worksheet as we did this. Have a great weekend.